My talk is going to be what I would have to call a little picture. Um, and you'll see that most of the errors that I deal with and the numbers that I'm talking about for Vision RT are a millimeter or less. So that I'm on the top of your tree in terms of where I hang out. So even though we use the Align RT system for body stereotactic, we use it for breath hold, breast. And what I'm going to talk to you tonight about is a lot of the measurements that I made to convince us that we, in fact, could use it for stereotactic work. And TriGEMS, which of course is the real challenge, the challenge. But I'll give you a lot of data on how the vision system compares to our gold standard, which is the LUTS test. That's going to be a large part of this. And then, anyway, we'll go into some other things. But so as physicists, you'll get to see the LUTS test kind of approach, and then how vision compares to it. So here we go. Let's see. I'm going to wander out here a little bit. So innovation-driven, precision. Where are we today, and where are we going to go? And I hope I can convince you of some of those things. So conflicts of interest, I really have none. There was no research funding for this, but the costs for my travel to this meeting were paid for by the Vision company. And I have some acknowledgments. Casey, sorry, it's going to be interesting. Casey Fitzpatrick is a radiation therapist at our clinic, and she's very demanding. That's one way to say it. And she really stopped me and said, don't drink the Kool-Aid. And this is when we were getting into using Align RT for stereo. That's how I like to say it. And it really forced me to study this thoroughly, at least as thoroughly as I could at the time. And that's what I'm presenting this evening. So she's not here, but I thank Casey. Also, Dr. Ben Waghorn is a physicist with Vision RT, and we've had Ben and I have had many emails and phone conversations. So thank you. I know Ben is here. Thanks, Ben. Stereotactic radiosurgery can be summed up in the parenthetical statement. Where are we? And can we stay there? I mean, that is the game. Do we know where the patient is, where the lesion is, and can we keep it there while we're treating? I mean, that is everything that we do. It used to be that we did it with a head frame, and we put 4 bolts in a patient's head. I did literally hundreds of those. But now, being more humane, we use a open face mask. And the same questions need to be answered, and that is, again, where are we, and can we stay there? The where are we part of it, we really answer with cone beam CT. But can we stay there? We now answer with Align RT. So you need to answer those questions and these questions. Where is the radiation isocenter in space? Can you place the tumor there? Which is a setup and positioning question. Can you keep the tumor there? And that, of course, is an immobilization question and a monitoring question. Again, this is where the Align RT comes in. And then finally, can we give some numbers, precision and accuracy to the answers to those questions? Well, if we had a perfect world, this is what it would look like. We would have our rotation axes of radiation isocenter being a spot in space, and our collimator rotation, gantry rotation, and couch rotation, they'd all be at one point. And then we, as physicists, could sleep a little easier. Of course, this is not a perfect world that we live in. And in fact, our rotations do not, in fact, have a point in space. Far from it. Well, within a millimeter. So where is the radiation isocenter in space? And the one answer for this is to use the Lutz test, which of course is decades old. And that, just to remind everyone, is a radiation image test to measure that position of the isocenter. It's based on radiological imaging, and it compares imaging of something that you know. In this case, it's the MLC edges, which I'll talk about, and it compares it to a test object. The MLC edges, that is what I've used as the reference object. And there's a lot that I'm going to say here in this, that the MLC itself is initialized by Varian software every day, but there's more to it than that. Of course, your MLC calibration, if there's a offset adjustment, there's a skew adjustment, you have to demonstrate to yourself that all of that, in fact, has been done correctly by your engineer. But if everything is done well, the centering of the MLC leaves is going to be plus or minus 1/10 of a millimeter every day, and that will be against the center of rotation of the collimator. My test object, I built. So I like to build things. This is as simple as it was. I actually have a steel ball. It's a 4mm ball in a plastic tube. It's embedded in Cerabin, so I can set it on the couch and it won't move and vibrate off. That is my test object. I look for that sphere in space. You can buy fancy things, but this does work. And the Lutz test images look like this. Here are the MLC edges, and there's the sphere, the 4-diameter sphere. And you're measuring the position of the MLC leaf edges with respect to the sphere to determine, and I determine where these positions are using free software. It's called ImageJ. I think probably a lot of you know about it. It's readily available. And you can use that to look at a image and determine edges and so on. And I wrote some simple Excel spreadsheet software for doing the analysis of the ImageJ data for determining the centers of that sphere and the centers of the MLC object or edges. And this is the sort of thing you see with this is a Trilogy machine. And this is a gantry angle, and these are error bars. The error bars are a half pixel. And this is the shift in the collimator central axis, SUPIMF with gantry rotation. And indeed, it is not a point in space. It varies by about plus or minus 4/10 of a millimeter. This is, again, a Trilogy machine. And this is based on the Lutz test. This is the shift of the collimator central axis left-right with gantry. And you can see it's much tighter. It's about plus or minus 2/10 of a millimeter, again for a Trilogy machine. And then finally, I'll show you some data. This is the shift of the collimator central axis. And this is ant-post with gantry angle. And you can see again, now this is a little bit more variation, but there it is. Again, that was versus gantry angle. There's your Trilogy, the numbers, sort of summary of the numbers, SUPIMF, ant-post. And we have 2 TrueBeams in our clinic, 1 Trilogy. The TrueBeam data, the machines are tighter, and SUPIMF for plus or minus 2/10 of a millimeter, ant-post the same, and left-right. The radiation isocenter is in the average position of all these shifts. So it's actually not a sphere in space. It happens to be a prolate ellipsoid, but it's this object in space. And we can measure that. In fact, I do measure it. We measure it more than annually. I've been measuring it once every couple of months to prepare a lot of data. But this is our typical Lutz test results, again, showing how that collimator center shifts in space. The LUTS test can also be used to look at the couch walkout in space. And the way that's done is the couch is centered, and then you actually look at how the sphere moves as you rotate the couch. So you establish the isocenter spot in space already done, as I showed for the gantry rotation, and now you look at what happens when you rotate the couch. The couch will walk out, and here's the kind of, again, it's the LUTS test, but now what you're doing is you're looking at the position of the sphere with respect to the MLC leaf edge as the couch is rotated. But the analysis is the same, it's just now you've changed your point of reference. And this is actually what occurs. You end up, what you find is the couch rotation center is not in fact at the radiation isocenter. Doesn't have to be. You'd like it to be, but that's not really where you'll find it. And the Align RT at radiation isocenter are here, and if you have a couch rotation center there, as you rotate the couch, guess what? Your isocenter will move away from your original point at 0 degrees. And again, your couch rotation then will shift anything on the couch off radiation isocenter, and it will also shift anything off Align RT isocenter. So you have to keep this in mind. That complicates where your lesion will be. You could have it right at that radiation isocenter, and as you rotate the couch, it'll walk off. And you have to know by how much it walks off. And that's the reason. So this slide shows our three machines. There's the 3455 TrueBeam. That's where that couch rotation point is. Here's another TrueBeam with its rotation point here. And then finally, here's our Trilogy. Amazingly, its couch rotation point is the closest to radiation isocenter, and of course, it's in a quite different spot. The lesson here is couch rotation points are unique to every machine, and in this case, amazingly, our Trilogy was the best. Some conclusions here. The LUTS test data shows that the sphere center shifts in space with couch rotation angle. The couch will walk the patient off of radiation isocenter even for the TrueBeam, and here's the range. Sup-imp, 0 to 1/2, left, right, 0.4. If you rotate the couch, the patient will walk off of isocenter. You absolutely cannot avoid it. And the cone beam CT at couch 0 is not valid at any other couch angle. It's valid at 0, but that's the only place. And I don't think everyone realizes that. So measurements with Align RT, the optical isocenter with Align RT, the radiation isocenter, and the way I check that, I'll show you. We have I'm shifting here from LUTS test to Align RT. The phantom setup is to radiation isocenter, and it's immobilized by bolting to the couch, and the movement is a 3D surface imaged by Align RT, and this is what it looks like. This is the reference cube, if you know the Align RT system, and this is used then to determine where the optical isocenter is, where the Align RT isocenter is, and then this is cone beam CT'd and compared to the radiation isocenter. So that is you have to know both, and you have to know where they are with respect to one another, and make them coincident. And in fact, there's a whole series of tests for Align RT for calibrating the isocenter, and you can make them coincident. There's some data. We in our clinic look at, for each machine, we look at the isocenter, the optical, Align RT optical isocenter, and compare it to the radiation isocenter. We do it every day on every machine. And here's the kind of data we have on one of our TrueBeams. This is 3 months of measurements, and here is our vertical, longitude, and lateral. These are the average differences between those isocenters over a 3-month period. And this is what it was for a Trilogy. So we're precise here in our isocenter coincidence on the order of 0.2 of a millimeter. And this, I show you 3 months data, but we've been doing this for almost 3 years. And if it does drift off, if we start seeing it drift, we check these data every day, then we will do a recalibration of isocenter. Can Align RT accurately measure the target walkout for when you rotate the couch? Here's the question. So the way this is done is I take Align RT reference images of a styrofoam head. I do couch rotations from 0 to 90 and 0 to 270, and then look at Align RT readouts and monitor them. There's the head. It's simple styrofoam. It is painted kind of a pink color. This was just done with some water-based paint from Home Depot. At first, I thought I was really worried about all really bright white styrofoam versus more of a skin color. As it turned out, it really didn't make much difference, but I show you the Phantom that we always use now. I think it was $12 on the internet, and the paint was $4 or $5, so easy to do. And this was a latex paint, water-based paint. The styrofoam head can be rotated with the couch, and this is mechanically fixed to the couch, so it doesn't move with respect to the couch. So this is just as if you have a perfectly immobilized patient that doesn't breathe, sneeze, blink, okay? So this is a test then of can Align RT track couch walkout that I showed you so nicely with the LUTS test. So here we go. Again, remember what's going to happen. We're going to rotate the couch, and if I have a rotation center here, my face is going to rotate off of isocenter. And can Align RT track that? There's the question. So, complicated slide, so let me help you here. Couch angle. The dots are the LUTS test. And by the way, these data have been they've been geometrically rotated into the Align RT space, which, by the way, rotates with the couch. So these are not in a coordinate system in the treatment room. They're the coordinate system of the patient as the patient rotates. So it's the Align RT coordinate system. So what we're seeing here is the longitudinal distance and how it changes with couch angle. Align RT, as you can see, differs from the LUTS test. I'm showing it in red. There's the Align RT data. Not too bad here, but pretty bad here. And this is in the lateral direction, a difference here at minus 75 and 90. And here it's after about 45 degrees, it deviates. So there's a problem where Align RT did not agree with the LUTS test. I communicated this, a lot of other physicists did, to the Align RT folks, and what happened was the Align RT company came up with a better way to calibrate the cameras. The original calibration was in a plane, and they came up with advanced camera optimization, and we did this in our clinic. The advanced camera optics calibration, in fact, calibrates over a volume instead of just a plane. So it takes into consideration a three-dimensional calibration instead of just a planar calibration. And now, in fact, there's really good agreement. Again, the dots are LUTS test, and that's Align RT. And you can see the agreement is within about 0.2 of a millimeter. And this is over wide, plus minus 90 degrees in couch angle. So indeed, the advanced camera optimization for the longitudinal direction really worked. And the worst case was lateral before, and now it's actually the best. So the answer here is Indeed, you do have couch walkout that you can measure with a Lutz test, and you can also now, within a couple tenths of a millimeter, get the same answer with Align RT, which makes you feel real good if you're looking at a patient and you're going to go to a different couch angle for stereo, and not just 0 degrees, but maybe 45-degree couch kick. Does Align RT tell you the right answer? And in fact, it does now if you use advanced camera optimization. Again, the differences in, oops, oh boy, there we go. The differences in Align RT compared to the Lutz test before advanced camera optimization were on the order as bad as 0.6 of a millimeter, and that's been cut in half. So we're now in the range of, these are just errors that we can't avoid. Where are we going from here? Well, the advanced camera optimization is going to be released to all clinics in a new version of software. This is another change. The rate of optical frame capture when you're looking at the patient is 10 per second, and that's going to be increased, I'm told, to 25 per second. And then finally, just the software itself, the workflow, I don't have slides on that, but it was not quite as intuitive as it's turning into the new version, so the software keeps getting improved. So some conclusions. The radiation isocenter in space for a true beam, this is the gantry rotation and so on, about plus or minus 0.2 of a millimeter. The couch rotation walkout can be as much as 0.5 of a millimeter, and that cone beam at 0 degrees is only valid at couch 0. Just keep that in mind. And before advanced camera optimization, we had differences on the order of 0.4 to 0.6 millimeters, and now that's been reduced to 0.2 to 0.3 millimeters. This really counts because if you rotate that couch and Align RT says to you, by the way, your patient has just moved 1 millimeter off isocenter. This is before advanced camera optimization. Back to 0, and you're doing a new cone beam. And we did a lot of those. But now, after advanced camera optimization, we rarely will see that. In fact, when we do, it's because the patient really did move. And when we go back to 0 and we'll do a cone beam, we'll see that, in fact, the patient has moved off isocenter, and we'll correct it. So the reliability of the Align RT system is really improved, and in fact has given us a lot more confidence in the clinic for how we treat our patients and how often we have to redo the cone beam CT. I didn't get into this, but there's enhanced linear accuracy as well as enhanced angular accuracy after the advanced camera optimization. The angular is really important for this reason. I think most of you know this, but I'm going to point it out. If you are treating multiple lesions with a single isocenter, if you have an angular error, the lesions will move off isocenter. Think about it. This is what it looks like. So, in fact, the distance between lesions will make a difference in how far it'll jump off isocenter. We use a rule of thumb. We'll take a 4/10 millimeter position error with an angular uncertainty of 1 degree. That means our lesions will be separated by about 5 centimeters or less. So we will not treat multiple lesions if they're separated by more than 5 centimeters. We won't treat them with a single isocenter. And this is the reason. Before advanced camera optimization, actually, we were half of this. The distance between them would be 2.5 centimeters, but now we've increased that to 5 cm. And the last conclusion is, for perspective, you got to keep this in mind. Even with the best mask, a patient, you'll still see breathing motion. If you look carefully, I hope, that they're breathing. And usually you can see it. You get really scared if you see no breathing motion. You know, you say, oh boy, I hope they're alive. You would like that to be the case after you do a stereo treatment. Even with a very good mask, especially a heavy patient, if they're 200, 225 pounds, I guarantee you, you will see breathing motion. And generally, it's on the order of 0.2 to 0.8 millimeters. And you can see it easily with Align RT. And then, of course, you need to make judgments. Call the, I get the physician over there, and we'll take a look at it. What margin did we use? Do we really want to treat this? Is it close to the brainstem? The questions start rolling. And we, in fact, have had patients that they're heavy and the breathing motion is large enough that we've seen it in Align RT, and we will just stop. No, margins aren't going to be adequate. We're not going to treat this today, and we'll replan. I mean, that has happened. We do it. And that's another use of Align RT in stereo, where you are monitoring the patient, and when you start to see differences on the order of 0.8 of a millimeter, you take a sober look at what you're going to do and you stop. And then you start thinking, talk to your physician colleague, what am I going to do? What do we really want to do with this case? Replan or not. But we are really using Align RT in stereo, and these numbers I'm showing you are real and comparable to a LUTS test. So that is the basic message, and you got to be careful, and you have to make a lot of measurements to convince yourself. Thank you.